So in the next hours, we're basically going to hire an AI to write an application entirely from scratch.
Yep, completely from scratch.
We're going to hand it the keys to provision its own cloud infrastructure. We're going to watch it build this highly secure, globally distributed network.
It's wild to actually see it happen.
And then we're going to use that exact infrastructure to host other AI models inside this totally isolated, airtight perimeter.
Right.
And the craziest part is we are orchestrating this entire thing starting from a completely blank black terminal screen. Welcome to the deep dive.
Thanks for having me.
Our mission today is a pretty intense one for you listening. We are going to map out the complete step-by-step architecture for a cloud-native web application on Azure.
And we're getting into the weeds on this one.
Oh, absolutely. Specifically, we're building an app that ingests images, right? And then processes them through this incredibly intelligent automated workflow where both humans and AI models inspect and report on them.
Exactly. And then it seamlessly updates a back-end source system.
Yeah, so it's a phenomenal architectural challenge.
It really is. And I mean, it represents a massive shift in how we approach enterprise design today.
Because writing code has gotten exponentially faster thanks to modern AI assistants.
Yeah.
Like, that's just a given at this point.
Oh, 100%. But the thing is, if you can generate an entire application stack in, say, 5 minutes, but you don't understand the underlying mechanics of, well, where to actually host it.
Right.
Or how to secure the perimeter, or how to trigger a back-end workflow without accidentally creating an infinite retry loop that just totally crashes your database.
Yeah, then all that speed is entirely useless.
Precisely. Today is really about bridging that gap. It's about the how and the why of modern cloud architecture.
Exactly. And let's set the baseline here for you guys listening. Assuming you know your way around a tech stack.
Yeah, you know what a virtual machine is, you know how basic web applications function.
Right, you understand standard deployment. What we're doing today is taking that knowledge and translating it directly into the Azure ecosystem.
Bypassing the theoretical textbook fluff.
Totally. We're looking at exactly how a senior cloud architect snaps these specific services together out in the real world. So let's just jump right into the terminal.
Let's do it.
Every workflow needs an entry point, right? Before we can process any images, we need our ingestion layer. We need the front end.
Yep, the front door.
So we're starting with an AI assistant to bootstrap this front-end web app.
And the toolkit for this initial phase is actually remarkably lean. Like, you don't need a ton of bloat.
What are we looking at?
Well, we start with the GitHub Copilot command line interface. If you're setting this up on your machine, you just invoke your package manager. So you type wingit install github.copilot.
Okay, simple enough.
Right, and appending the -- pre-release flag ensures you have the latest experimental capabilities. But you have to remember that Copilot on its own is really just a generalized large language model.
Right, it's basically locked in a box.
Exactly. It understands code syntax perfectly, but it doesn't inherently understand the real-time state of your specific Azure subscription.
Right, or the exact syntax of Azure Resource Manager APIs.
Okay.
Because it only knows what was in its training data, right?
Right.
It can't natively reach out and check if, say, a specific storage account name is globally unique, or what resource groups you currently have deployed.
Precisely. And that is where the real breakthrough happens with this stack. It's called the Model Context Protocol, or MCP.
Okay, MCP, break that down for us.
Think of MCP as a standardized, secure bridge between the lockbox intelligence of that LLM and the live external environment of the cloud.
Okay, so you're giving it eyes and ears.
Basically, yeah. You're giving the AI a very specific, highly constrained set of tools and vocabularies. By typing MCP add followed by the Azure MCP server, you're essentially plugging an Azure translation engine directly into Copilot's brain.
Wow.
Yeah, and when you run MCP show, you can actually verify the exact toolkit the AI now has permission to use.
So it can now read your local configurations and dynamically draft accurate cloud commands based on your actual environment.
Exactly. And to round out the toolkit, you just bring in the Azure Developer CLI, which you invoke via ASDID. We're going to rely on that one heavily when it comes time to package and deploy.
Okay, so our terminal is primed. The AI is officially hired and trained on the Azure blueprint. Now comes the prompt.
The fun part.
Right. So we ask Copilot to, and this is a really highly specific directive, we say, create an app for a photo album blog gallery where I can upload my photos, as well as delete and move them between various albums.
Then you have to specify the stack.
Right, we specifically request React for the front-end UI and Node.js with Express for the backend.
Which is a super standard modern stack.
Totally. But what's fascinating here isn't just that it writes the JavaScript. I mean, we've seen it do that for years now. It's how the Copilot CLI actually processes the directive through these different operational modes.
Yeah, the operational modes are basically a masterclass in AI and human collaboration.
How's
Well, it starts in interactive mode, right? Which is a conversational state where it just parses what you actually want.
Okay.
But the critical step is that it immediately transitions into planning mode.
Oh, so it doesn't just start writing code blindly.
Exactly. It does not just start wildly generating files. It analyzes the dependencies. It maps out the required abstract syntax tree for all those React components.
It figures out what it actually needs to build first.
Right. It determines the API routes needed for the Express server, and then it dynamically drafts a plan.md markdown file.
See, I love that mechanism. It forces the AI to essentially document its architectural intent before it executes a single line of code.
It's like asking a contractor for a blueprint before they start pouring concrete.
Exactly. It hands you this plan.md and basically says, hey, here's the component tree I'm going to build. Here are the REST endpoints I'm setting up. And crucially, here are the Azure resources I intend to provision to make this whole thing run.
Yep. And then you, the human architect, review it. If the logic holds up, you shift it into implement mode. Or if you're feeling brave and want to take the guardrails off entirely, you engage autopilot mode.
And what does that do?
That lets it execute the entire plan sequentially without stopping to ask you for continuous confirmation at every single step.
Which is fast. But we'll get to the risks of that in a second. So when it executes that plan for the infrastructure, we see it provision the initial requirements locally.
Right. It establishes a resource group.
Which is basically the fundamental logical container in Azure, right?
Yeah.
Where all your related application resources share a unified lifecycle.
Exactly. If you delete the resource group, everything inside it goes with it.
Got it.
So inside that group, it provisions a storage account. And because we're dealing with unstructured data, raw image files, it specifically leverages the blob service within that storage account.
Right. Bypassing tables or queues because it's just raw files.
Yep.
Okay, wait, hold on. I need to pull the emergency brake for just a second here. Autopilot mode sounds great for speed, I'll admit. But if I am letting an autonomous AI agent spin up cloud resources, modify my local file system, and authenticate against my actual Azure subscription.
Yeah, it sounds terrifying.
It really does.
Yeah.
How is this not a massive security incident waiting to happen? I mean, what stops Copilot from assigning itself global administrator rights or going rogue and modifying resources in a completely different production resource group?
That is the exact right question to ask. And it highlights exactly why the model context protocol is engineered the way it is.
Okay, made me feel better about this.
It heavily enforces the foundational security principle of least privilege.
Right.
When Copilot drafts the configuration to interact with that newly created storage account, it does not use a blanket owner role. It doesn't even use a contributor role at the subscription level.
Because if it had contributor access.
It could delete your entire database if it hallucinated a bad command.
Right. Which we absolutely do not want.
Exactly. Instead, the MCP enforces really tight boundaries. Copilot specifically assigns itself the storage blob data contributor role.
And that's scoped exclusively to that single storage account.
Exclusively to that one storage account. It grants itself only the exact cryptographic permissions required to read, write, and delete blob data within that specific container, and absolutely nothing else.
Wow, okay.
Yeah, it cannot modify the networking rules of the storage account, it can't access other storage accounts, and it certainly cannot touch your broader Azure Active Directory configurations.
Okay, that is a massive relief. It is functionally the difference between giving a contractor the keys to the entire office building versus giving them a smart badge that only unlocks the specific supply closet they were hired to paint.
Right, and only between the hours of 9 to 5.
Exactly. Okay,
Yep.
so the infrastructure is defined safely. Copilot pulls down the node packages, writes the React components, and we have a working local build.
You test it on localhost?
Right, you upload a JPEG, maybe the local Express server throws a CORS error, you tell Copilot to fix the proxy middleware, and it iterates.
Standard local dev stuff.
But a local app dumping images into a local emulator is just a toy. We have to push this ingestion point onto the real internet securely.
We have to go live.
Right. So this is the transition from local development to production architecture. How do we do that?
To facilitate this, we bring in the Azure Skills plugin from the marketplace.
Azure Skills. Okay.
Running the command skills list reveals a dedicated suite of deployment tools right in your terminal. And this is where the asdup command comes into play.
I love ASDUP.
It's incredible. It's a highly opinionated, heavily automated command. It basically takes your source code, containerizes or zips the assets depending on your configuration, and deploys it directly to an Azure App Service plan.
Let's drill into the app service plan for a second, just to be clear on the architecture. We aren't spinning up a raw Linux VM and configuring Nginx or Apache manually here.
Oh, definitely not. App Service is platform as a service, or PaaS.
Right. So you're abstracting away the operating system layer entirely.
Exactly. App Service handles the load balancing, it handles the SSL termination, and all the underlying patch management. You don't worry about any of that.
You are essentially just renting a slice of compute power dedicated entirely to serving your application code to the internet.
Yep. But the deployment itself introduces a really critical security pivot that we have to talk about.
Okay, what is it?
When you were testing locally, the code was likely using your local Azure CLI developer credentials to talk to the backend storage.
Right, my personal credentials on my machine, which is fine for my laptop.
But if Copilot just zipped up your environment variables and pushed them to the public cloud?
And those variables contained a hard-coded connection string or a storage account key.
Yeah, that is exactly how massive data breaches happen.
Yep, if someone scrapes the app service, they suddenly have the keys to the kingdom.
Because hard-coded secrets are basically the enemy of cloud security.
Precisely. So to solve this, the architecture transitions immediately to using a managed identity. Okay, managed identities.
The deployment instructions force Copilot to strip out any reliance on static credentials. It configures a user-assigned managed identity instead.
Let's really map out the mechanics of a managed identity for a second, because I think people hear the word identity and they just think, oh, it's a different kind of password.
Yeah, that's a common misconception.
But it is fundamentally passwordless,
Yeah.
right? Like, how does the app service actually prove to the storage account who it is without a secret key or a password?
It's pretty brilliant. It relies on the underlying Azure Fabric and Microsoft Entra ID.
Okay.
When you assign a managed identity to an app service, Azure essentially registers that application in your Entra ID tenant as a first-class citizen.
Like it's a real user.
Right? And behind the scenes, the Azure platform automatically generates and securely rotates the cryptographic certificates required for authentication.
Oh, so the platform manages the keys.
Exactly. You, the developer, never see these certificates. They cannot be exported. They cannot be leaked in a GitHub repository because you don't even have access to them.
So when my Node.js backend tries to upload a photo to the blob storage, what actually happens on the wire?
Well, the code makes a local HTTP call to a hidden endpoint that Azure injects into the app service environment. It basically says, hey, Azure, I'm this application. Please give me a token to talk to storage.
Okay, and Azure checks its ID.
Right. Azure verifies the environment, checks Entra ID, and returns a short-lived JSON web token, or a JWT.
Got it.
Your application then attaches that temporary token to its request to the storage account. The storage account checks the token, sees that this specific managed identity has that storage blob data contributor role we talked about, and allows the right operation.
That is just brilliant. It's a completely closed loop. It's like a VIP hotel key card for the app itself. It doesn't use a username or password that could be stolen. The building just inherently knows this application belongs there.
That's a perfect analogy. But I do want to point out, I noticed you specified a user-assigned managed identity earlier rather than a system-assigned one.
Right, yes. What is the architectural difference there?
Yeah.
Why one over the other?
A system-assigned identity is intrinsically bound to the life cycle of a single specific resource.
Meaning?
Meaning, if you create an app service and give it a system-assigned identity, and then a month later you delete that app service, the identity is immediately destroyed along with it.
Which sounds super convenient at first.
It does, until you realize that if you had a database relying on that specific identity for access,
Oh, no.
and you recreate the app service, your entire backend is now completely broken because the old identity it trusted no longer exists.
Because it creates brittle architectures.
Yeah.
You've hard-linked the security to the compute instance.
Exactly. A user-assigned managed identity, however, is created as an independent, standalone Azure resource. You manage its lifecycle completely separately.
So it's decoupled.
Right. You can assign that single identity to your app service, your backend Azure functions, and your virtual machines all simultaneously.
Okay, I see the benefit there.
Yeah, it allows you to establish centralized role-based access control RBAC rules, a perimeter that persists even if you tear down and completely rebuild the underlying compute resources.
Speaking of tearing down and rebuilding, that brings us to the final piece of the deployment phase.
Mhm.
Because Copilot isn't just pushing code, right? It is explicitly instructed to generate a bicep file.
Yes, Bicep.
For anyone who hasn't worked with infrastructure as code, or IAC, Bicep is Microsoft's domain-specific language for deploying Azure resources. But it's fundamentally different from just writing a PowerShell script
Radically different.
because it's declarative.
Exactly. The distinction between imperative scripting and declarative code is basically the foundation of modern infrastructure.
Break that down for us.
Well, an imperative script is just a list of sequential commands like step 1, create a storage account. Step 2, if it exists, do nothing.
Okay.
Step 3, now create an app service. Now configure core.
Right, just a checklist.
And it's incredibly fragile. If the script fails halfway through, you are left in this unknown, broken state.
But a declarative bicep file doesn't give instructions on how to build things.
Right, it doesn't care about the steps. It just describes the final desired state.
Okay.
You write a file that basically says, my environment must contain an app service with these exact memory limits, a storage account with these specific redundancy settings, and a user-assigned identity linking them.
And then you just hand that file to Azure.
You hand it to the Azure Resource Manager. Azure calculates the delta between what currently exists in reality and what your file dictates, and then it executes the exact, highly parallelized API calls required to make reality match your file.
That is so powerful.
Oh,
Because it makes the entire environment instantly reproducible.
exactly.
If a rogue administrator goes in and manually deletes the storage account by accident,
Yeah.
you don't have to scramble to remember how to rebuild it. You just re-execute the bicep file, and Azure puts it exactly back where it belongs.
It guarantees environment parity across development, staging, and production. You're never guessing if the environments match.
Okay, let's look at the board so far. We have a live front-end application hosted on PES. It's secured with a passwordless, token-based managed identity.
Yep.
And we have our infrastructure codified in Bicep. When a user uploads a photo, our backend perfectly authenticates and drops that image file into an Azure storage blob.
The ingestion layer is officially complete.
Right. But right now, that data is just resting there. It's totally inert.
A storage blob doesn't do anything on its own.
Exactly. How do we transition from static storage to an active, intelligent workflow? Like, how do we wake the system up and tell it to actually look at the image that just arrived?
This is where we need event-driven architecture.
Event-driven, okay.
It's the absolute moment that data lands, we need the system to react without human intervention. And the primary compute engine for reacting to discrete events in Azure is serverless compute.
Specifically Azure Functions.
Yes, Azure Functions.
Now, serverless, we have to clarify this because the terminology is notoriously misleading for people new to cloud. There are absolutely servers involved here.
Oh, of course there are servers. Under the hood, it is massive racks of physical servers in a highly air-conditioned Azure data center.
Right.
Serverless is simply a billing and operational abstraction. It means compute on demand.
Okay, so contrast that with the old way.
In a traditional infrastructure model, you deploy a virtual machine, you install your middleware, and that VM sits there spinning 24 hours a day.
Burning money.
Exactly. If your photo application gets absolutely zero traffic at 4 a.m. on a Sunday, you are still paying for the CPU cycles and the RAM just to keep the OS running.
But Azure Functions invert that model entirely. You don't provision a server. You just write a highly specific, discrete block of code, a function.
And you bind that function to a trigger.
Oh, that's
In our architecture, the trigger is a blob storage event.
because it's waiting for an image.
Right. Through deep integration with Azure Event Grid under the hood, the exact millisecond a new photo is successfully written to our storage container, Azure detects the state change.
It knows a file arrived.
It instantly allocates compute resources, pulls your function code, injects the metadata of the newly arrived image as the payload, and executes the code.
So our function wakes up, reads the image, maybe it extracts the EXIF data, the GPS coordinates, the timestamp, the camera model.
Yep, the heavy lifting.
It takes that extracted metadata, writes a new record into a back-end database, and then the function just terminates. It shuts down.
And the financial beauty of this model is microbilling. You are billed purely for the execution time and the memory consumed, measured in milliseconds.
Wow.
When the function isn't running, it costs you absolutely nothing.
That sounds like an absolute dream for scalability and cost management. But let's explore the dark side of event-driven architectures for a minute.
There's always a dark side.
Right. If we are triggering a script on every single upload event, we're introducing a massive structural risk. The concept of an event storm terrifies developers for a really good reason.
Oh, it really does.
What happens if there is a flaw in our logic?
An event storm is a catastrophic failure cascade, and it's exactly why defensive coding is a strict requirement, not just a friendly suggestion for Azure functions.
Okay, walk us through a hypothetical scenario. Let's say things go wrong.
Imagine a batch upload where a user drops 10,000 images into the blob storage all at once.
Okay, huge batch.
Event Grid detects 10,000 events and instantly spins up 10,000 concurrent instances of your Azure function.
So far, so good, right? That's what it's supposed to do, scale out.
Right, that's the cloud working perfectly. But your function code is designed to write the metadata to a backend database, right? Let's say Azure Cosmos DB.
Okay.
Cosmos DB operates on provision throughput, which is measured in request units. If 10,000 concurrent functions hit a modestly provisioned database simultaneously,
Database is going to freak out.
Cosmos DB will protect itself. It will begin rate limiting the requests. It will start throwing HTTP 429 errors.
Too many requests.
Exactly.
Okay, so the database rejects what happens to the function instance.
The function encounters the unhandled 429 error and it crashes.
Right.
But because this is an event-driven system, Event Grid assumes the processing failed due to a transient network blip, and its default behavior is to automatically retry the execution.
Oh, no. So Event Grid immediately fires those 10,000 events right back into the function engine.
So the functions spin up again, hit the database again, get rejected again, and fail again.
I see the loop. If you have 10,000 events and the default retry policy is, say, 5 attempts, you just turn 10,000 executions into 50,000 executions in a matter of seconds.
Precisely.
And because you pay for every single execution, your compute bill is just skyrocketing, while your database is essentially being subjected to a friendly fire-distributed denial-of-service attack by your own infrastructure.
It is a nightmare scenario, and this is exactly why you must implement defensive mechanisms.
Like what?
You need exponential back-off in your retry logic, meaning the system waits progressively longer between attempts 1 second, then 5 seconds, then 20 seconds.
Giving the database time to catch its breath and recover.
Right. But more importantly, you absolutely must implement dead letter queues.
Dead letter queues. Explain that.
If an event fails 3 times, you don't keep hammering the system. You gracefully route that specific failing event payload into a secondary separate storage queue for manual review later.
Okay, so you quarantine it.
Exactly. And you let the primary function shut down cleanly so it stops racking up charges.
Okay, so we added our guardrails. The Azure function securely and efficiently extracts the metadata and writes it to the database. But our ultimate goal is an intelligent workflow, right? We need humans involved in this loop.
We do.
We need an inspector to actually look at this image, approve it, or reject it. So my question is, are we supposed to write thousands of lines of custom code inside our little Azure function to handle email protocols, capture human responses, and manage state timeouts?
You could, technically, but it would be a massive architectural anti-pattern because functions are designed for stateless, rapid compute. They execute and die in milliseconds. They are not designed to pause and stay alive for 3 days waiting for a human to click approve in an email.
That would cost a fortune.
Exactly. For that, we introduced the orchestrator, Azure Logic Apps.
Okay, logic apps. This is where we shift from heavy coding to more visual orchestration, right?
Yes. Logic Apps is a declarative workflow engine. While a function is all about writing code to manipulate data, a logic app is about defining a state machine to route that data across different systems.
Got it.
It utilizes this vast ecosystem of over 1,400 pre-built, fully managed connectors.
So instead of me writing a complex API integration to talk to Office 365, I just drag an Office 365 connector onto a visual canvas, authenticate it, and tell it to send an email.
It is completely low-code integration.
Oh.
So in our scenario, the architecture looks like this. The Azure function finishes its heavy compute task extracting the metadata, and then it fires a simple HTTP webhook over to the Logic app.
And hands off the baton.
Right. The Logic app takes over. It uses an Office 365 connector to generate a beautifully formatted email containing a secure link to the image and an approve or reject button.
Okay.
The logic app then pauses its execution. It literally suspends its state in the background, which costs next to nothing.
Because it's not actively running compute cycles.
Exactly. When the human inspector finally clicks approve in their inbox, the logic app wakes back up, captures the response, and uses a database connector to update the final status in Cosmos DB.
So it's really about the separation of concerns.
Precisely.
I use Azure functions for the custom complex business logic, the actual data parsing, the mathematical transformations, the image resizing. And then I use logic apps for the high-level orchestration, the routing, the third-party integrations, and the human-in-the-loop interactions.
It's the perfect balance. It allows your core developers to stay deep in the C# or Node.js code where they are most efficient, while allowing business analysts or integration architects to visually design and monitor the overarching business process without needing to write a line of code.
That is a phenomenal ecosystem. Okay, we have ingestion, we have compute, and we have human orchestration. But we promised you listening an AI inspection workflow as well.
Yes, we did.
What if human inspection is just too slow? What if we want to run these newly uploaded images through an advanced computer vision model to automatically detect sensitive content, say, identifying personally identifiable information or flagging inappropriate imagery before a human ever even sees it?
This is where we run headfirst into a massive enterprise compliance wall.
Oh, compliance, always the roadblock.
Right. Let's assume these images are highly sensitive. They could be medical scans, proprietary manufacturing diagrams, or unreleased financial documents.
Stuff that absolutely cannot leak.
We cannot take that sensitive data, package it up, and send it over the public internet to a shared, public Azure Cognitive Services endpoint.
Right. Even if the connection is perfectly encrypted, sending highly regulated localized data out of our tightly controlled virtual network into a public, multi-tenant AI service is just a non-starter for most compliance officers.
It violates data residency instantly.
And it introduces unacceptable egress risks. So how do we leverage cutting-edge AI without the data ever leaving our secure perimeter?
We bring the compute to the data.
We invert the model.
We invert it entirely.
Right.
Instead of sending our images out to the AI, we pull the AI inside our network. And the vehicle we use to do that is Azure Container Instances, or ACI.
Okay, containers. Let's pause and elevate this concept for a second.
Yeah.
We all know virtual machines provide total isolation by running a complete guest operating system, a full Linux kernel, all the system daemons, everything sitting on top of a hypervisor.
It is robust, but it is heavy.
Right. Containers are a completely different paradigm.
A container is a lightweight, executable package of software that includes everything needed to run an application. The code, the runtime, the system tools, the libraries, the settings.
Everything except the OS.
But crucially, yes, it does not include the operating system kernel. Containers running on a single machine share the host OS kernel.
Which makes them so much smaller.
Exactly. This makes them incredibly fast to start and highly efficient in terms of memory and CPU.
And Azure Container Instances is essentially serverless containers, right?
Yep.
You don't have to provision a virtual machine to act as the host. You don't have to install Docker yourself. You just hand Azure the container image, and Azure runs it directly on their managed infrastructure.
It is the absolute fastest way to spin up isolated compute in Azure.
So how does this solve our AI compliance problem?
Microsoft actually allows you to download specific cognitive services like the computer vision API or the language detection models as prepackaged Docker containers.
Wait, really? You can just download the AI?
You can. You take that Microsoft-authored AI container and you deploy it into your own Azure container instance, explicitly injected into your private virtual network.
Oh, this is fascinating. Let's trace the network path on that.
Let's do it.
So the image arrives in our storage blob. Our Azure function wakes up. Instead of calling the public URL for Azure OpenAI or Azure Computer Vision out on the internet,
the function makes a local HTTP call to the private IP address of the ACI container sitting right next to it on the same internal subnet.
that is incredible. The container receives the local request, executes the complex neural network inference entirely within the isolated memory space of that ACI instance, and returns the JSON result back to the function.
And the raw image data literally never touches the public internet.
It never crosses a regional boundary.
Exactly.
But wait, I have a logistical question. If the container is running completely offline inside my private network, how does Microsoft actually charge me for the AI service? I know these models aren't free to use.
It's a brilliant architecture. The cognitive container is designed with two distinct interfaces.
Okay.
The primary inference API, where you actually send the images for processing, is strictly local. It does not have internet access whatsoever. However, a secondary, very lightweight sidecar process runs alongside it. This process only aggregates usage metrics.
Ah,
It basically says, I processed 50 images today, consuming X amount of compute. Periodically, this metering sidecar reaches out to a specific billing endpoint in the Azure Cloud.
and reports the usage.
Right. It sends the billing telemetry, but it was cryptographically impossible for it to send the payload data.
Wow. So you get the absolute privacy of an on-premises, air-gapped system, but with the operational pay-as-you-go billing model of the public cloud.
It is the silver bullet for regulated industries. You
Yeah.
literally drop a fully equipped, portable AI forensic lab directly into your secure basement.
That is just so cool. Okay, so our workflow is incredibly sophisticated now. The image comes in, the function triggers, it securely calls the local ACI container for AI inspection, gets the result, and if it fails the AI check, the Logic app emails a human security officer.
Right.
If it passes, it writes to Cosmos DB. We have built an absolute masterpiece, assuming we are processing, what, maybe a few hundred images an hour?
Which brings us to the inevitable pivot point in literally any successful application's lifecycle: scale.
Scale. The hardest part.
What happens when your application doesn't just succeed but goes globally viral? What happens when you are suddenly processing millions of images per minute across 3 different continents simultaneously?
A single Azure container instance is going to buckle instantly. I mean, ACI is brilliant for discrete, isolated tasks or sudden burst workloads. But if we need 500 containers running simultaneously, ACI just lacks the structural management to handle that, doesn't it?
It absolutely does. If you manually deploy 500 ACI instances and 30 of them crash due to random memory leaks, who restarts them?
Nobody. They just sit there broken.
Right. How does the Azure function know which of the remaining 470 containers are actually available to accept traffic?
It doesn't.
If you need to roll out an update to the AI model without taking the entire system offline, how do you manage that rolling upgrade? ACI simply cannot answer those questions. It lacks orchestration.
And the undisputed king of container orchestration is Kubernetes.
It is.
In Azure, this is AKS, the Azure Kubernetes Service.
Kubernetes is a platform for automating deployment, scaling, and operations of application containers across massive clusters of hosts. It is basically the complex brain that manages the fleet.
Okay, break down the AKS model for us.
In AKS, Azure manages the control plane. That's the API server, the scheduler, the underlying database that tracks the state of the cluster. Azure provides this control plane highly available and fundamentally for free.
So what are we paying for?
You only pay for the agent nodes, which are the actual virtual machines that your containers run on.
Got it.
Right. With AKS, you don't define individual containers manually. You define a deployment.
Okay.
You tell Kubernetes, I need a deployment of my AI inspection model, and I need you to guarantee that there are always exactly 50 instances of this container running.
And then Kubernetes just makes it happen.
Kubernetes constantly monitors the cluster. If an underlying virtual machine hardware fails, taking down 10 of your containers, Kubernetes instantly detects the discrepancy between your desired state of 50 and the actual state of 40.
And it fixes it.
It automatically spins up 10 new containers on healthy nodes to replace them without you lifting a finger.
It is totally self-healing. And it also solves the auto-scaling problem, right? We can integrate something like Kita Kubernetes event-driven auto-scaling.
Yep, Kita is incredibly powerful.
We can tell the cluster, hey, monitor the queue of incoming images. If the queue backs up to more than 1,000 pending items, dynamically scale the AI containers from 50 up to 200 to clear the backlog. And then scale them back down to save money when the queue is empty.
Exactly. To truly grasp the magnitude of what AKS can accomplish, let's examine a real-world implementation.
I love real-world examples. Let's hear it.
Consider the architecture required for Mercedes-Benz to push over-the-air, or OTA, software updates to their global fleet of connected vehicles. Oh, wow, okay. We aren't talking about a simple photo gallery anymore. We are talking about life-critical firmware updates for cars driving on the highway.
Precisely. Historically, updating a car's software was a completely hardware-driven, manual nightmare.
Yeah, you had to take it to the shop.
It required the owner to physically drive the vehicle to a dealership, plug it into a diagnostic machine, and flash the internal systems. It happened maybe once or twice a year max.
Mercedes transitioned that entirely into a cloud-native microservices architecture driven by AKS. Let's trace the data path of a global vehicle update because this is mind-blowing.
Let's do it.
So the engineering teams build the new firmware or application logic, and they compile it into a container image. They push this image into a highly secure Azure container registry.
Right. Now, the metadata about that update, which specific car models need it, the cryptographic hashes to verify it's legitimate, the version dependencies that metadata is not stored in the container registry.
Where does it go?
It is pushed into Azure Cosmos DB. Ah, okay. Because Cosmos DB is a globally distributed multi-model database.
Exactly. When Mercedes writes the metadata to the primary Cosmos DB instance in Europe, the Azure backbone automatically asynchronously replicates that data to Cosmos DB instances in North America, Asia, and everywhere else they operate.
Ensuring single-digit millisecond read latency regardless of where the car is physically located on the planet.
Yep. So the data is staged globally. Now the car wakes up. The vehicle's head unit connects via a secure cellular network. It sends an API request saying, hey, I'm in S-Class in Seattle. What is my update status?
And where does that request go?
That request hits Azure Traffic Manager, which is a DNS-based load balancer. Traffic Manager analyzes the geographic origin of the request and routes it to the closest regional AKS cluster.
So it routes Seattle traffic to a West Coast data center.
Right. An orchestration microservice running inside that AKS cluster receives the request, queries the local low-latency Cosmos DB replica to check the metadata, determines that the car absolutely needs an update, and then securely pulls the required containerized update from the registry and streams it down to the vehicle.
The scale of that is just staggering. Millions of cars executing complex orchestrations across the globe, handled entirely by AKS and Cosmos DB.
It is.
It took them from yearly hardware updates to continuous cloud-native delivery.
And you know what the most impressive metric is? The development velocity. By moving to this containerized orchestrated model, they built the initial functional prototype in 24 hours.
You're kidding.
24 hours. And they shipped the entire production system to market in just 3 months.
Okay, I hear that. It's an incredible architectural feat. But as the host, I have to represent the developer who is listening to this right now and feeling completely overwhelmed.
Fair enough.
Let's be real. Kubernetes is notoriously difficult to configure.
It is a steep learning curve.
It introduces a massive operational overhead involving node pools, complex CNI networking plugins, ingress controllers, and pod identity management.
Yep.
If I am just building our image ingestion app, even a highly successful one, am I not completely over-engineering this by defaulting to AKS? It kind of feels like buying a freight train to deliver a pizza.
That is a phenomenal analogy, and your pushback is completely justified. Defaulting to Kubernetes for every single project is a widespread anti-pattern in modern tech.
Right.
Architecture is always an exchange. It is a calculation of trade-offs.
What exactly are we trading here?
With AKS, you get unparalleled cloud-native flexibility. You avoid vendor lock-in because Kubernetes is open source.
Yeah.
You could lift those containers and move them to AWS or on-premises relatively easily.
Okay, and you get massive global scale.
Right. But in exchange, you accept the heavy responsibility of operational ownership.
The maintenance.
You are responsible for upgrading the Kubernetes control plane versions. You must manage the OS patching of the agent nodes, and you have to design the complex internal security perimeters using network policies.
So what is the actual rule of thumb? When do we pull the trigger and buy the freight train?
If your application architecture consists of 20 or 30 distinct microservices maintained by 5 different development teams, and those services must scale completely independently of one another, that is when you need the orchestration power of AKS.
Makes sense.
But if your application is a straightforward monolithic front-end, backed by a simple API and a linear background workflow like our image gallery, do not use Kubernetes.
Just do it.
Stick to the PaaS offerings. Use Azure App Service for the front end, Azure Functions for the compute, and ACI for the isolated AI. Abstract the management away so you can focus on the business logic.
Let's follow that advice. We are going to stick with our specialized, component-based PaaS architecture. Let's step back, clear the board, and lay out the final, ultimate workflow architecture.
Let's bring it all together.
We have a lot of pieces here. Copilot generated the React front end. We have managed identities, functions, logic apps, ACI, and Cosmos DB. Let's snap them all together into one unified enterprise-grade system.
Synthesizing the components is really where the true value of cloud architecture emerges. We begin at the perimeter, the front end. As we discussed, this is hosted in an Azure App Service.
Right.
It provides the fully managed web environment perfectly suited for our React user interface. It scales dynamically based on HTTP traffic, serving the application to the end user.
So the user uploads the image through that app service. The image lands securely in the Azure Storage blob, and this triggers the middle tier.
The middle tier is the logic engine. This is where Azure Functions wake up.
Cool.
The function acts as the initial processor, extracting metadata and making the critical routing decisions. If the image needs intelligent inspection, the function makes a secure local network call to our Azure container instance.
Where the AI model evaluates the content without ever exposing the data to the internet.
Exactly.
And if the AI flags the image, the function triggers our orchestration layer, Azure Logic Apps, which handles the asynchronous process of notifying the human security team and waiting for their manual review. And ultimately, all the approved metadata, the AI scores, and the workflow state are persisted in the backend layer. Azure Cosmos DB, providing us with a globally replicated, high-performance data store.
It is a highly robust system.
It really is.
But there is one foundational layer we have explicitly omitted until now. And in a real enterprise environment, without this layer, the entire system is critically vulnerable.
You are talking about API management.
Yes, I am. Azure API Management, or APM.
So where exactly does this fit into our architecture?
It sits squarely between the front-end app service and the middle-tier Azure Functions.
Let's visualize this, because right now, our React front-end is making HTTP calls directly to the Azure Functions to submit data or request the gallery feed, right?
Which means the URL for our Azure Functions is technically exposed directly to the client browser.
Which is a massive risk. If the front-end can see the function URL, so can a malicious actor. They can bypass the front end entirely and start hammering your back-end APIs directly.
Which is exactly why API management acts as the ultimate enterprise bouncer.
I love that. The bouncer.
Before any request from the public-facing app service can reach the back-end functions or the logic apps, it is intercepted by the APM gateway.
So let's break down what this gateway actually does, starting with authentication.
Well, the first thing the bouncer does is check IDs.
Right.
APM intercepts the incoming HTTP request and immediately looks for a JSON web token in the authorization header. It actively validates that token against your Microsoft Entra ID policies.
What's checking for?
It checks the signature, verifies the issuer, and ensures the token hasn't expired. If the token is missing or invalid, APM rejects the request with a 401 unauthorized before the request ever touches your backend compute.
So your functions don't waste precious CPU cycles and money dealing with unauthenticated garbage traffic.
Exactly.
Okay, so the user has a valid ID, but the bouncer also does a weapons check.
Right. In architectural terms, we are talking about Layer 7 protection.
The application layer.
The gateway sits at the application layer of the OSI model. It can be integrated with a web application firewall or WF. It actively inspects the payload of the request itself.
So looking for.
Is there a malicious SQL injection script buried in the form data? Is there a cross-site scripting attack hidden in the URL parameters? APM identifies these threat signatures and neutralizes the request instantly.
It also handles rate limiting, right? Because even if the user is authenticated and safe, we don't want them uploading 5,000 images a second and triggering that event storm we discussed earlier.
Precisely. You define throttling policies directly in APM. You can say, hey, this specific user or this specific subscription tier is only allowed 100 API calls per minute.
Okay.
The gateway tracks the state. On the 101st call, APM returns a 429 too many requests. The backend Cosmos DB is completely shielded from the surge.
And finally, the bouncer handles the routing. The front end doesn't need to know the specific URLs of the 50 different Azure functions that make up our backend.
No, that would be a nightmare to maintain.
The front end just sends everything to like ap.rgallery.com/upload. APM receives it, inspects it, and internally routes the traffic to the correct backend destination. It completely decouples the client from the microservices.
And to make this architecture truly impenetrable, we combine API management with the ultimate networking feature, private endpoints.
Let's explain the mechanics of a private endpoint, because this is where the magic of Azure networking really shines. Even with APM in place, our Azure functions technically still possess a public DNS address resolving to a public IP, right? They're just relying on AP and to block unauthorized traffic.
Correct. But a private endpoint fundamentally changes the network topology.
How so?
When you configure a private endpoint for your Azure function or your Cosmos DB, Azure literally injects a virtual network interface directly into your private VNet. It assigns a private IP address, say 10.0.0.5, to that specific PAGS resource.
And then it removes the public internet routing entirely.
Exactly. It manipulates the DNS zone. The public URL of the function no longer resolves to the public internet. It resolves exclusively to that internal 10.0.0.5 address.
Wow.
This means the front end, the APM gateway, the functions, the logic apps, the ACI containers, and the Cosmos database are all communicating securely, exclusively over the private Microsoft backbone network.
It creates an airtight, dark architecture. A malicious actor scanning the public internet won't even be able to find the IP address of your database, let alone attempt to log into it.
They can't even ping it.
They have to come through the front end,
Yeah.
get authenticated by Entra ID, get inspected by API management, and then be privately routed inside the VNet.
It is the absolute pinnacle of defense in-depth architecture. And it perfectly encapsulates the value of this entire deep dive we just did.
It really does.
You don't have to use every single tool for every single job. If you are building a weekend prototype, you don't need private endpoints and APM, but knowing how to synthesize these tools.
Right, knowing how to snap together the Copilot CLI for rapid generation, Bicep for reproducible infrastructure, functions for cheap compute, logic apps for human visibility, ACI for secure AI processing, and APM for perimeter defense.
That is what separates a developer who just writes code from a master architect who designs real systems.
It is about knowing the entire palette of options available to you, understanding the deep technical trade-offs of each one, and painting the exact solution your specific business problem requires.
Let's just summarize the immense journey we just took.
Let's do it.
We started with nothing but a blank terminal window. We utilized the Model Context Protocol to teach GitHub Copilot the exact rules of our Azure environment. We watched an AI dynamically generate the infrastructure, enforcing least privilege via strict RBAC roles, and write the React and Node code for an image ingestion application.
And then we transitioned from local development to a production cloud architecture. We deployed the front end to a managed app service, stripping out hard-coded secrets and relying entirely on the passwordless token exchange of user-assigned managed identities. We solidified that environment using the declarative power of Bicep infrastructure as code.
We moved from static storage to active, event-driven workflows. We explored how Azure functions trigger on blob events, and we dissected the catastrophic risks of event storms, emphasizing the critical need for dead-letter queues and exponential backoff.
We separated our compute logic from our stateful orchestrations by introducing Azure Logic apps for those human-in-the-loop approvals.
We tackled the massive compliance hurdles of enterprise AI by bringing the compute directly to the data. We deployed cognitive AI models inside isolated Azure container instances, ensuring highly sensitive image data never once traversed the public internet.
We evaluated the pivot point of extreme scale, looking at how Kubernetes and AKS utilize a managed control plane and agent nodes to coordinate massive global deployments, referencing that incredible Cosmos DD-backed architecture of Mercedes-Benz connected vehicles.
And finally, we locked the entire system down. We introduced Azure API Management as our Layer 7 gateway to handle authentication, WAF inspection, and rate limiting. And we sealed the network perimeter using private endpoints to ensure all traffic remained exclusively on the private Azure backbone.
It is a comprehensive, bulletproof, production-ready architecture.
It represents the absolute cutting edge of how enterprise systems are designed and deployed today.
It really does. But before we sign off, I want to leave you, the listener, with a provocative thought that builds on everything we've just discussed today. Think about the underlying reality of the system we just built. We learned how to use an AI GitHub Copilot to analyze requirements, draft architectural plans, and autonomously generate the complex, secure infrastructure required to host and orchestrate other AI services, our containerized cognitive models.
It's AI all the way down.
Exactly. If an AI is already capable of understanding virtual networking, enforcing least privilege, and building the highly secure, globally scalable homes for other AIs to live and work in, what exactly will the role of the human cloud architect be in 5 years? Are we destined to remain the master builders, or are we rapidly transitioning into building inspectors, simply reviewing the blueprints drafted by our AI contractors? It is something to seriously consider as you design your next system. Thank you for joining us on this deep dive. Keep questioning the architecture, keep building secure systems, and we will see you next time.